Hello! What I'm going to do today is a curved mirror problem with curved mirror and an object really close to the mirror. If you remember when we saw the really big mirror in class, if you looked at yourself in it, you were upside down, and that was a concave mirror real image, but then when I put my hand really close to the mirror, my hand was upright. So that's a different type of image, and that's the one I'm going to do today. It's called a virtual image, and so we have a concave mirror virtual image. We're going to have the same setup as we had before. So I need my axes. Whoop. There's my horizontal axis. And now I'm going to start to get sloppy on my mirrors because we draw everything to the straight line behind it. So I don't really care how curvy I draw it. I can be sloppy. There's a mirror. Okay. And I need my vertical axis right behind the mirror. Ooh, that's a little... Okay, so we need a vertical axis behind the mirror, and that's that's where I draw most of my lines too. And we need to mark off where the center curvature and the focal length are. And now, you know, if you can just make it up what this curvature looks like, because I'm going to give you the situation. So in this case, I'm going to put my center curvature way out here because I'm going to have an object close up. Now center curvature is, ooh, wow, pretty good, 50 centimeters. So my focal length is going to be half that right there. Mirror, axis, center curvature, focal length. Got it set up. Now I put my object somewhere close in. So in this case, I want my object to be closer to the mirror than this. All right, so object right there. And again, it doesn't really matter what your mirror looks like. So I will make it a full mirror though. There you go. That would bother me. So here we have our object, and light rays are going to leave the object. Some of them are going to bounce off the mirror, and then we want to find out where the image is going to be formed. All right, so let's figure this out. I need a shorter object actually. Let's make a shorter object. There. Okay, so concave mirror again, we know where the focal length is. It's the same three rays that we did the last time. So our first ray comes out parallel to the axis and goes through the focal. So we have a ray coming out parallel to the axis, and then it goes through the focal. All right, that's roughly straight. Yeah, Okay, our second ray is the tricky one. So for the second ray, normally we would have it go from the object through the focal, and then it would go leave the mirror parallel. The order is just reversed. So instead of going from here to here, we're going to start at the focal and have a ray go through the object that way. So it really is, it's the same ray as we had before, just the order is different. We're going to go F to object to mirror. All right, what does this look like? F to object to mirror. And then when it leaves the mirror, it is going to be going out parallel. Maybe something like that. Okay. So that's ray 1, out parallel, through focal, ray 2, through the focal, out parallel, and then we've got ray 3, which goes through the center curvature. And that's the easy one because it just goes on itself. All right, so through the center curvature and through our object. And it bounces right back off on itself. Okay, so there's our three rays. And, well, okay, do the three rays that leave the mirror ever meet? Nope. We have these three rays leaving the mirror, and they are never going to meet on this side of the mirror. Where will they meet? Well, if you think about it, they would have a meeting point somewhere back here. This is what we call a virtual image because it's not, the light rays don't actually go through the mirror to create an image back here. It's virtual. It's only something that can be seen in our eyes. If I put a piece of paper here, you wouldn't be able to see anything on the screen. With a real image, you could put a piece of paper there and see something on it. Virtual image, well, I mean, clearly, if I have a mirror and I put a piece of paper back here, I'm not going to see anything. So what we do is we backtrace the rays, and now we've got a lot of rays here. If you look at this, there's 1, 2, 3, 4, 5 rays. The ones that we want to backtrace are the rays that leave the mirror. So it's this one, and this one, which is why I tend to draw those little arrows saying, these are the ones that are leaving. So I'm going to trace these backwards behind the mirror. And I usually do this as a dotted line, dashed line, just to remind myself that the light rays don't actually exist back here. It's only our brain being fooled into thinking they exist. Okay, so I want this one. All right, so center curvature. Whoop, how are we doing here? Oh, let's see how this one goes. Well, 2 of them are matching. And now the trick. Does the third one match? I'm hopeful. All right. Ooh, not too bad. Not too bad. Okay. So when we backtrace all 3 of the rays that are leaving the mirror, we actually do see they converge back here. Now, again, it doesn't mean there's an actual image here. This is a virtual image. The light rays aren't going through the mirror. Our eyes are fooled into thinking that the light rays are meeting back here. So what can we say about the image? Well, it's definitely taller. So when I put my hand in front of the mirror, the image in my hand should be bigger, and it was. Okay, so we have a larger image. It's a little bit farther behind the mirror than the object was in front. Okay, and well, that's about it. So there's our virtual image. Nothing is formed over here. We have to backtrace them to find where they meet. We can do the same measurements and equations as we did before. So I will need to make some measurements. DO is my object distance. That's object to mirror. And in this case, we have object to mirror is 12 centimeters. So that's, oh boy, I don't even know how to label this. DO is from here to here. Image distance is image to mirror. And then we have to have some special way to mark that it's a virtual image. It's behind the mirror. So we expect the image to be formed over here. That's a real image. When it's behind and it's a virtual image, what we do is we say that this has a negative image distance. It's on the kind of the negative side of the mirror. So my DI is going to be from here, mirror, to my image. And I'm going to give it a negative sign because it is virtual. 19, 20, let's say 19. And then I'm going to say negative. My focal length is from the focal point to the mirror. What do we have there? 20, 1, 2, 3, 4. Yeah, I'll call it 25. So a focal of 25 centimeters. And then we can use our equation again to figure out where the DI actually is. And then we need our height of the object, HO, is going to be this height. So the height of the original object is 5, 6, 7, 8 centimeters. And then we will be able to calculate what the image height should be. So I'm going to measure it and then we'll be able to calculate it. So measured is, what do we have, 14, 15, something like that. Around 14 and a half, how about that? So what I want you to do is use our equations, the mirror equation, 1 over DO plus 1 over DI equals 1 over F, to figure out what DI is. And in one step, DI is 1 divided by focal minus 1 divided by DO. So use this equation with F and DO to calculate what DI is, and you should come up with a negative, should be around negative 19, and then use our magnification equations to figure out, oops, that's a positive there, negative DI over DO, to figure out what HI is. And it should be close to, oh, you know what, I should be careful here. Last time it was negative because it was below. This is above the axis, it's on the same side. So this should end up being a positive value. And so calculate HI, it should come close to a positive 14, 15, somewhere around there. So virtual image, and what else do we have? We know it's larger and it's upright. It's not inverted. So this image, larger, upright. So larger means that my magnification should be bigger than 1. And upright, I'll just remind myself, larger means magnification bigger than 1. And my magnification should be positive to make it upright. So those are both different than what we had last time. Whereas with a real image, we had a magnification smaller than 1 because the image was smaller, and we had a negative magnification because the image was inverted. So because it's larger, I would expect a magnification bigger than 1, and because it's upright, I should have a positive magnification factor. So use these two numbers. Once you have DI, use DI and DO to get your magnification. Once you have your magnification, use M and HO to figure out HI. And that is a virtual image from a concave mirror. So same ray tracing, same equations as a real image. It's just that a real image is formed out here somewhere, and the virtual image is behind the mirror. And that's all I've got for you. Okay, good job.